Hello and welcome. Now we will take up a simple and classic problem, and the problem is a cylinder with adiabatic walls is closed at both ends. That means no exchange of heat from the surrounding, and is divided into two volumes by a frictionless piston. Friction is also absent. The volume, pressure and temperature of the ideal gas in each side of the cylinder are equal to V0, P0 and T0 respectively. Everything is in equilibrium, I guess. A heating coil in the right hand volume is used to heat slowly the gas on the side until the pressure reaches to 64 P0 by 27. It is 64 upon 27 times of the initial pressure. Okay. If the heat capacity, specific heat capacity at the constant volume, we call it Cv of the gas, is independent of temperature, it must be, because these are very much sensitive things to change in temperature. So this is a good information and we are going to use it. And Cp by Cv, which is equal to the adiabatic exponent gamma, is equal to 3 by 2. Find the following in terms of V0, P0 and T0. The first thing is to find the entropy change of the gas on the left side. Okay, the final left hand volume, the final left hand temperature, the final right hand temperature, and the work done on the gas on the left. Problem is not very much complicated. It's a simple problem. Main thing is piston is thermally insulated as well. So that means no heat can enter the left hand side. And since no heat can enter the left hand side, then the entropy change of the gas on left hand side must be 0. So this is the answer of first problem. It is 0. And as far as second part of the problem is concerned, the left hand volume, we need to find out the left hand volume after the heating coil is inserted into right hand volume to heat it slowly. That means the right hand side expands and left hand side contracts. Piston might have moved from this position to this position, and everything has been changed now. The left hand side might have pressure P1, volume P1 and temperature T1, and in the similar manner the right hand side may have pressure P2, volume P2 and temperature T2. And both sides of it, the left hand I need to consider, the final left hand volume we need to find. So this left hand side, it is completely thermally insulated. No heat can enter. That means its compression must be adiabatic. It is compressed, so its compression must be adiabatic. And that means we can write the equations like this. Is initial pressure, though we can use PV gamma equals constant, the adiabatic equation, and we can write simply like V0, B0, gamma, that will be equal to P1, V1, gamma. And I guess we already have the pressure value in the new condition, because in the new equilibrium the pressure in the left hand and right hand sides must be equal. This should have been, otherwise equilibrium has not been reached. That means I guess pressure in the both sides, P1 and P2, but I would like to write here P1. P1 is something given in the problem, that is 64 P0 by 27. So we know the P1 and we need to find the result in terms of V0. So P0, that means we got V1. V1 can be written simply as V0 P0 by P1 raised to 1 upon gamma, and gamma is 3 by 2, so we can write here V0 P0 by P1 raised to 2 by 3. And since P1 is 64 by 27 P0, that means V1 becomes V0 27 by 64 raised to 2 by 3. And you can calculate this and you will get 9 V0 by 16. This is the left hand volume in the new equilibrium. And now we need to find out something else, the final left hand temperature. And this was the solution of the part B of the problem. And left hand temperature, so what do you need to, how can we find the temperature thing? We should be back to the ideal gas equation, that is called PV equals nRT. And we can be sure of this, that number of volumes of the gas, number of molecules of the gas in the left hand side must also be constant during the compression, because there was no opening. They were covered by a piston, adiabatic piston, and that means N remains constant. And N is constant, that means PV upon T is a constant in this process. And we are looking for the left hand side temperature, so we can write here initial conditions P0 B0 by T0, and that must be equal to P1 V1 upon T1. And we know the value of V1 and we know the value of P1. P1 is simply 64 P0 by 27, and V1 is 9 upon 16 V0, and we can get the value of T1. And T1 is simply P1 V1 by P0 V0 T0. And after putting the values, you can get T1 equals 4 T0 by 3. So what about the second last problem, the final right hand temperature? And this is also easy to calculate, because we know that total volume of the gas is constant, and it is 2 V0 initially, and it will be finally when V1 becomes V0 becomes V1 and V2, that means the total volume remains constant. So we know the value of V1, we can find the value of V2 as 2 V0 minus V1, and that will be 2 V0 minus 9 by 16 V0, and that you will get 32 minus 9, 23 upon 16 V naught is the value of V2. And again we need to find the temperature of the right hand side temperature, and this is quite simple to find. If we again use that number of molecules of the gas in right hand side also remains constant, we can again use PV by T equals constant for right hand side of the piston, and we can write the equation like P naught B naught by T naught equal to P1 or P2. P2 is equal to P1, so either we can write P1 or P2. So I would like to write P1 here, P1 V2 by T2, and we know the value of V2, we know the value of P1, and we can calculate T2, and T2 is going to be P1 V2 by P naught V naught T naught. And after putting all those values, you are going to get T2 equals 92 by 27 T naught, and that is the answer. And what is the right hand side? What is the last problem? This is the work done on the gas on the left. Since the process is adiabatic, so from first law of thermodynamics, Q is equal to 0. That means change in internal energy plus work done by the system equal to 0. And work done is equal to negative of change in potential energy. That is minus NR delta T, NR by gamma minus 1 delta T. We know the value of gamma as well, but we don't know the value of N, though we can find, but this is simply P naught T naught by V naught, P naught V naught by T naught, but you can also write NR delta T is equal to delta PV, and you can write it like this, delta PV by gamma minus 1, and delta PV, and a minus sign is here, so that will be simply like P1 V1 minus P naught V naught by gamma minus 1, and putting all those values you can get your result. So though this value will come in minus sign, that means work is being done on the gas. This is not the work done by the gas, and the question in this problem was what should we take the minus sign? Work done on the gas. That means the numerical value obtained from this expression will be enough, and it must be minus, so you will finally going to get the result as 2 P naught P naught by 3. It's the simplest of the problems. Only we need to know what to use, when to use. And thank you very much for watching.